Hello everyone, today we discuss contest 16. I'm pre-recording this video because I will be out of Cyprus when I publish this. So I don't know the final results, but already obvious that a contest is a little bit harder than I expected, especially the last problem probably. So nobody solved the last problem. Mm, okay, so it's like I've solved it after the contest. It's good for you, yes. It's actually a good thing to solve the problems even if you don't solve them during the contest, then solve them after the contest. It's very good. So also problem D is much harder than I expected. Yes, maybe I missed something. I will read your solutions. So we will go to problem D. I will read your solutions and we will see. Maybe I'm missing something. Maybe it can be solved easier, but my solution is pretty complicated. Yeah, oh, and that's it. Problems F and G are actually not that hard as it may look. We'll see. So we'll go to problem F and G. I'll tell you how to solve them. They are not that especially hard. Problem H is fun. Okay. Problem D. Okay. Problem D is not really hard, but I would say it's too professional maybe. Yeah. So if you know data structures and stuff like this, it's kind of obvious. But if you're not, then maybe tricky. So okay, let's go discuss all the problems. So again, I solved all the problems before, so I will just show you my screencast and how I solve these problems. So problem A. Problem A is kind of easy, but again, it's kind of geometry problem in some sense. So you may be a little bit scared of geometry. So what's happening problem A, we basically need to count the distance on a two-dimensional plane. So we have number of points in two-dimensional plane. They specify some broken line, and you need to calculate the total length of this broken line. Not actually, nothing hard in this. So you just go split this half-life into segments and then calculate the length of the line as sum of length of these segments. And to calculate the length of the segment, you use Pythagorean theorem. So it's just square root of sum of the squares of differences by x and difference by y. So here you can see I calculate difference by x, difference by y, and calculate distance as the square root of the sum of the squares. So you can see that. So I'm just using so it's basically using the Pythagorean theorem to calculate the distance. There is actually a special function in C++ called hypot. It does specifically this. So you just call hypot of these two differences, and it will give you the length of the hypotenuse of these two sides. So it's you can use it like this, or you can use just explicitly use square root of sum of two squares. Both will work pretty fine. So in the end, if you don't know this, in C++, if you by default it outputs two little signs. So in this problem, it's not matters because you need to have precision up to 10 power 6. You see this, and okay, so it will be enough without this. But just as a good habit, I always put, it says precision 20, so I always output at least 20 digits. So 20 is enough. It's more than actually C++ can handle. So I output all the digits that they have. So it's maximal precision possible. And you can see here I missed something. I quickly checked what I missed. So I don't need to output length. I need to length divided by 50. Why not? So I divide the length by 50, and that's it. So that's it. That's problem A. Again, probably a little bit too much for the first problem, but again, nothing really difficult in this problem. Just read the data, understand what's going on, calculate some distance using some mathematical formulas. Nothing really that difficult, but again, some geometry involved, some programming involved. So that's it. That's problem A. Let's move to problem B. So in problem B, we have elevator, and we need to count the maximal time we need to transfer all the passengers down. And there are multiple ways to do it. So since you travel only down, so you can just go down and simulate the process. You can stop at every floor, wait for all the passengers on this floor, move next, wait for all passengers, and so on. You can do it like this. I would implement a little bit more simple solution. So what I will do instead, I will not wait for all passengers. I will just wait in the beginning and then move to the end. And I just look for the, so if I move to the end, I just grab all the passengers because they're already ready. So I grab all the passengers and move down. And you can see that the maximal time you need, the total time you need to to get all the passengers is just equal to sum, or to the maximum time for every single passenger. So for every single passenger, the time we need to put them to the floor 0 is just sum of f plus t. Yeah, so it's floor t. So it started at time t plus we need time f to move them to the first floor. And so we need to calculate maximum of all these sums. And don't forget to put this s here. Yeah. So I initialize my minimum as s, because if I don't have any passengers to wait, I just need to go from floor s to floor 0. And it's also special case you need to care about. Besides that, that's the full solution. Quite simple, I would say. So this is the whole solution for problem B. Yeah. Yeah, no, okay, it's not pure implementation, but again, you need to find the way to implement it this simplest way possible. Yeah, that's what I did. If you implement it a slightly more complicated way, that's okay still. Okay, let's go to problem C. Okay, problem C again. I believe the main difficulty is problem to understand what's going on in the statement. A very simple actually problem. So we have some number of lines. In each line we have some gnome, and we have dwarf, and we have some candy. Okay, so we have dwarf and a candy, and the dwarf moves to the candy. So every time we start the game, all the dwarfs move to the candies to the right, and as soon as one of them reaches the candy, we stop, and then again start the process again. And you need to calculate number of these stops you will have. So you start the process, it stops, you start again, it stops again. So it's easy to see that number of it's a number of times you need to start this process is just equal to number of different lengths, different distances from dwarfs to candy. So if two dwarfs are at the same distance to the candy, they will reach it simultaneously. Yeah, and that's it. So what we need to do is calculate number of different distances from dwarfs to candies. And sometimes you output -1 if dwarfs is to the right from the candy. Yeah. So what I'm doing here, I just use this function find, why not, to find the position of the dwarf, position of the candy, and here, okay, here I'm interested what C line. So C line shows me some warnings, so I usually check what's happening. Maybe C line knows something better than me. Sometimes it does. Here it's actually not a big problem. Yeah, so I see if the dwarf to the right from the candy, I output -1 and immediately stop. If not, I add all these distances to my set. It's just the easiest way to calculate number of different elements in yours. So just put them in a set and look at the total size of this set in the end. You can just put them in an array and sort it, or just multiple ways to do it. That's just easiest way. That's why I'm doing it like this. So that's basically it. That's problem C. Okay, so actually a lot of people solve this problem, so you're not scared of long problem statement. That's good. That's good. That's it. Let's go to problem D. Problem D is actually interesting. So first of all, problem D is scary because it introduces some strange formula right in the middle of the problem statement. So you need to read this, read the problem statement, read this formula, and not be scared of it. Okay, try to teach yourself not to be scared of formula in the problem statement. So sometimes problem authors put some strange formulas in the problem statement just to scare you. Yeah. So if you see something like this, just try to read it multiple times and get the some intuitive feeling of what this formula does. Yeah. So in this case, what this formula does? So it's actually written in. So it's good for them. So they actually wrote it in words. So this f of n is product of non-zero digits of 10. Sometimes, if problem authors are less kind than these ones, so they will put some special formula here, so make it even more scary. So f of n is just product of non-zero digits of n. It doesn't look very scary actually. Now g of n is just again. So what's happening here? We just apply recursively for function f. So g of n is the same as g of f of n. So we recursively calculate product of digits, get the result, again calculate product of digits, and so on until we have number less than 10. So we have single digit. So we have single digit. This is the result. That's it. So this is function g. We apply product of digits until we have a single digit. That's it. So it looks like it's called digit root when you calculate sum of digits. Yeah. Digit root is just remainder modulo 9 if you don't know, but here we have product of zero digits. That's different. Yeah. So we have some strange function here. And what we need is to answer the queries. Query is given a segment and the value. We need to calculate number of integers in this segment with the specific value of k. And what you're doing in problem like this, you first look at the constraints. Yeah, that's the first thing you look at. So when you read the problem statement, then you immediately look at the constraints, because constraints actually define what solution we're looking for. Yeah. So let's see. So I have a lot of queries. Let's see. Sorry, I'll stop me doing. I'm calculating here. I'm calculating looking at the number of queries. Number of queries is kind of high, so I can't answer all the queries. I just pretend. And here L and R. So this length of my segment is up to million. Yeah. So you can't answer all the queries just naively. Yeah. But this L and R up to 10 power 6, up to million. Million is not that much actually. You can iterate over values over million. You can have array of size million. So million is not scary. Yeah. You can have array of size million and it's not be a problem. Yeah. So now you think, okay, if I just have this problem, you try to simplify the problem basically. Yeah. So you have this function. Okay, I need to calculate. I have basically array, yeah, array of values of size million. Doesn't look scary yet. And then in this array of size million, I need to calculate number of values in a specific segment. This problem is not very scary. So again, so what we need to calculate? So you have, imagine you have arrays. So you have array g, not function g, but array g. Yeah. And you're given a segment of this array, and you need to calculate number. Okay, okay. Number of values k in this segment. This problem is not really scary, right? So what you can do, for example, you can do one way to solve this problem. It's quite well-studied problem. Yeah. So sometimes you need to calculate number of something in a segment. You can use, for example, the following technique. So for each value k, you can maintain the set of all values k. Yeah. So you can put all different values in different containers. Now what you need to do for this container, you need to look for values in your segment. You can do it, for example, using binary search. So you can put all these positions in specific arrays. So you can make like list, let's say list of 4k. Yeah. So it will contain all positions of value k. Then in this list, you look for all position in a given segment. You can do it using binary search. Yeah. So you call this binary search, find number of elements here, and that's it. Or you can do it differently like I did. So you can see that number k is kind of small. So instead of having containers, you can just make 10 containers of size n, and it will also be fine. So instead of having I will make several containers. Let's call them, I don't know, let's say A, K. So in this container, I'll just put ones in positions of k. So for all elements are zeros, except values k. So values k will be ones, all other elements will be zeros. And now we just need to calculate sum on a segment in data structure for value k. So for each k, I will maintain this vector of ones and zeros, and I need to calculate sum on a segment. Sum on a segment is just difference of two prefix sums. So I will calculate prefix sum, take this prefix, subtract this prefix, get sum on a segment. Yeah, and I can do it because k is small. Yeah, if I would have the same problem but with large value of k, I would use this technique. So I will make so again, in this technique, I put only positions for each value, I remember only positions of this value. So like total size of these lists is n. Not n, but this maximal coordinate. Yeah. So if I have this big value of k, I would do it like this. Yeah. But since I have only small values, I can have 10 arrays of size million. So in total size 10 millions still will be fine. Yeah. So again, 10 arrays of size million, so it's like 10 millions element, and each element I believe uses like of integers, so like 4 bytes of information. Yeah. So I need like 40 megabytes of data. Yeah, that's very small amount of data. You can handle it easily. Yeah, even if you have 100, you can, okay, 400 megabytes. It's okay. It depends on the problem. Some problems have like 255, 56 megabyte limit. So, but if you have gigabyte limit, you can have 100 array like no problem. Uh, that's it. So let me finish the problem. So what I'm doing here? Uh, First, yes. Also, you need to calculate the function. Yes, so you need to get from the function to the array. So I will basically calculate my function g for all values from 1 to million. Yeah, and here I'm making the array. So here I make an array of size million. I make it of size million 1 because I want to have indexes from 0. Yeah, so I have indexes from 0 to million. 0 will be 0. We don't care about it. Yeah, but I have indexes from 1 to 0 will be my important digit. Uh, it's okay. Can scale have million 1. If you're not sure which value you put here, just put million 10. 10 will be enough always for problems like this. I just know I need one extra element, so I put 1 here. I just calculate function. This I use something like dynamic programming. Yeah. So I go from left to right and calculate all the values. So so here in this part I calculate function f. Yeah. So I basically split my number into digits, calculate product of all non-zero digit, and copy the value gs to my gi. Yes. So my value will be the same. So I basically calculate value f. Yeah. And put gn equal to j of f. Yeah. So basically go from left to right, calculate all values of function g. Yeah. Now I will create 10 prefix summaries. Why not? Oh, actually 9. I create 10 because I can. Yes. Prefix for 0 will be just not used. Yeah. So I use only values from 1 to 9. Well, that's it. It's just normal prefix sums. Yeah, go from left to right. Like normally I do, a prefix sum isn't exclusive. So a prefix sum of I include all elements to the left from the I, from 0 to I minus 1. So prefix sum of 0 is always empty. Prefix sum of that's it. Okay, here I made a mistake. I cannot move L to R to 0 notation. Like I usually do, I use from L to R to 0 notation, but in this problem I actually use 1 notation because I can. So here I don't need, okay, that's why I have this 5. Big thanks to authors, so they actually put this good example. So here I moved L to 0 notation. I should actually use R plus instead. R plus. So so this is sum from L to R inclusive in one notation. Yeah, that's it. So that's it. That's how I solve problem D. Okay, maybe a little bit too much for problem D in this kind of contest, but sometimes it happens. Sometimes problem D is not that trivial. So you have to actually do several steps: calculate function, calculate suffix, prefix sum, stuff like this. Maybe problem E is actually easier in this contest. It happens. Sometimes problems are not sorted by, or so usually problems are sorted by the difficulty, but difficulty is subjective. Yeah. So some people say this problem is more difficult, another may say this problem is less difficult. So if you see the problem and you're not sure how to solve it, you can just skip it and go to the next problem. Yeah. Maybe next problem will be easier for you. Just or maybe you will you go back and then you have some idea. So just to load some more problems to your brain, so your brain start working in the background. Okay? It actually helps a lot. I actually want to read your solutions for problem D. Prefix sums. Yeah, I see prefix sums. I see. No, exactly. Okay. So here I calculate all the numbers. I calculate them recursively because you can. You have the same recursion. Okay, I can calculate them recursively. Нет, you have memorization here. Okay. So you do it in basically linear time. If linear number of executions of this function. Then you have prefix sum, again, all the same thing, but you did it quite fast. Good for you. Let's check someone else. Okay, and you doing this second approach I discussed, yeah. So for each value, you maintain the vector of positions, yeah, here. For every value, you put now positions. And here you calculate, you use binary search twice. You will calculate upper bound, lower bound, and that's it. So difference will be number of elements. Yeah, good for you. So that's the same solution, but with different data structure. Yeah? Calculate number of elements in this segment. You can do this. Also works. Good, good. So problem E. Problem E is kind of easy. So yeah, I would say it's much easier than problem D. So what we mean problem E, we need to construct number with given length and given sum of digits. And we want to find the maximal minimum number of this kind. And it's I think it's kind of obvious how this number should look. So if you have if you know the sum of digits and you want the maximum number to be maximal possible, you just put all the big digits to the beginning. Yeah. So you put some huge digits in the beginning, so you have 99999, then something what's the remainder of nines, and then zeros. Yeah. So number should look something like this. And well, let me draw actually. So if you construct maximal number, it should look something like this, called 999, then some remainder of 9, let's say, and then zeros. Okay? Something like this. And if you want to find the minimal number, you want to put all these nines to the right. Yeah. But you can start with 0. Yeah. So the first digit should be at least 1. So you put 1 here. And then you put this 9999 from another end. And here you have like 2. Yeah. So that's basically the idea how you construct these numbers. Now you need to carefully implement this because first number may be not 0. So if you have big sum, this position would be close to here, so this number will be not 1. You need to increase this 1 to some position, and so on. But it's just now it's just all about careful implementation. I implemented a very easy way. I just, again, when I calculate minimum, I start from this number. Then I go from right to left and try to increase these digits as much as possible. And when I start from maximal, when I calculate maximum number, I go from left to right and start from this position and increase number from this. I can also start from the same position here. It will not be a problem. So again, you start from some number and then go either from left to right or from right to left and increase all the digits while you can. There are also some special case here. I solved some special case. Do not forget special case when you have s equal to 0. Yes, it's kind of tricky. So s may be equal to 0, and it's actually in an example. So you see, so the authors actually make you see that s may be equal to 0, and you need to think what will happen if s equal to 0. And you see that s equal to 0 is impossible if m is greater than 1. But if m equals to 1, there is number 0. Okay, number 0 is tricky. It's kind of special number which has leading zeros and it's kind of allowed to have leading zeros. Yeah, so that's it. So that's one special case equals equal to 0. Also some cases when you have impossible. So I usually track all the special cases before and then track all the general case. That's basically it. So I will just go from left to right. Here I will go from left to right. Yeah. When I calculate maximal value, just go left to right, and here, as you see. So I try to so C is the sum I need to spend. So I go from show me the code. So C is the number of digits I have to spend. So I go from left to right and see if digit is not 9 and I have some extra sum to spend. So I put it here. Yeah. That's it. It's not the fastest code. Yes, I put I track some one by one. I can instead of this while I can calculate this value and rest. Let me show you. So instead of doing this while, I can just count how much I can add to this digit. It's minimum of 9 minus di and c. So it's how much I can add to this digit. So instead of this while, I just can calculate and do it in one step. but it actually will not improve my solution that much. So my while can make it at most 10 steps. 10 steps of while is very fast actually, especially in modern C++. They have all this conveying thing. So it's usually not a problem to have small loop of like 10 iterations instead of something. So if I have time, if you have time limit, you can then think how to optimize it. But in this problem, you will not have time limit because you have actually all the constraints are kind of small. So if you can solve problem easier, even the less optimal solution, try to do it to optimize your time, not computer time. Yeah. So if you fit into time limit your solution, that's it. So just stop optimizing it. Yeah. Let's go to problem F. Problem F is actually not a very hard problem, but it involves some combinatorics. No, actually, pretty simple combinatorics. We need to use binomial coefficients. It's quite popular in odd conforces to have problem which involves some binomial coefficients in the calculation. What we have here, so I didn't draw any picture, so let me draw it here. So what we have in problem F, we have, let me see. So we have so we have two digits, and so, again, pay close attention to the constraint. So n is small, n is up to 10 power 6. 10 power 6 basically means you can make array of size n, or you can make n iterations. So you can iterate once all numbers up to n. And you think, okay, I can iterate all numbers up to n. That's nice. So again, you're looking for numbers of size n, which consist of digits a and b. So you have digits a and b in some order, yeah? And you need sum of these digits be a good number. Okay, what is the sum of these digits? No, you can count, okay, the sum of these digits do not depend on order of these digits, yeah? So you have some number of digits a, let's say x, yeah? So sum of these digits will be x multiplied by a plus n minus x multiplied by b. And it doesn't depend on order of these digits. So what I can do, I can iterate on numbers. So x can be from 0 to n. And I can just brute force all possible values of x because n is small. So again, pay attention to the constraints. If you see some small constraint, small like million, yeah. So if you have 1,000, you can iterate 2 parameters, yeah. If you have million, you can iterate 1 parameter at least, yeah, or even multiply by some log factor. Yeah? So that's what I do. I will calculate. I will iterate all values of x, calculate sum, check if it is good. If it is good, then I can just rearrange letters a and b. Yeah. So number of ways to rearrange letters b is just binomial coefficients of say so. Okay. Usually, it is how we write in Russian literature. It's written like this. Yeah. Yeah. So it's number of ways to choose x elements out of n. Yeah. And you calculate it using factorials. Okay. If you never did it before, just learn how to do it. It's not very hard thing to do. So you just calculate factorials, inverse factorials, and then calculate binomial coefficient like by dividing one factor by another. You can divide modulo prime if you calculate inverted values, and you calculate inverted values by calculating number modulo or in power p minus 2. Let me draw it again. So again, factorial is okay. So this value is n factorial divided by x factorial and by n minus x factorial. And when you need to divide, you basically use the fact that like a in power minus 1, basically 1 divided by is equal that a in power p minus 2 modulo p. That's how you divide in prime modulo. And you calculate power by binary exponentiation algorithm. Very easy actually. Normally I would copy it from my library. I have all these formulas in my library, obviously. But here, since we have time, I just implemented it from scratch. So let's see. So this is basically the whole algorithm. So what I'm doing here, I look at for all values of x, calculate sum s, check if sum s is good. If s is good, then I will calculate my binomial coefficient and add it to the result. Okay, here I'm just careful to not have any integer overflow problems. And here I just do Just add it to the result. Come on. Yes. Just add this value to the result. So I calculate binomial coefficients from n to x. That's it. So in the end, I just output the result. Now I don't forget to calculate everything modular. So now it's a boring part. I will just, yes. And I will just implement all the, can we speed up actually? I don't know. How to speed up in VLC? Can I speed up? Because it will be kinda forward effect. I don't know how to speed up in C++. Playback. Oh, you can do. Let me speed up it a little bit. So I will just implement all the combinatoric stuff. So here I calculate binomial coefficient by just calculating factorial of n divided by factorial of k, and then divided again by factorial of n minus k. Okay? So here I calculate number of ways to choose k element out of n. That's it, easy. Okay. Now I need to count all the factorials. Yes, so I will do it here. I need factorials up to n, so I create array of factorials upside n plus 1, so from 0 to n inclusive. And here just calculate all the factorials. Do it even faster. X2. Yes, and here I'm doing it like this. So you can calculate inverse factorials by inversing all the values, or you can calculate the last inverse factorial and then calculate it from right to left by multiplying. So I don't have to call the inverse function n times. It's just faster than just normally do. It would still work in this problem. I'm kind of sure. So you can calculate inverted like million values. It's fine, but I just usually do it like this, so I can show you how to do it. So that's it. So again, here I calculate factorial, and here I calculate inverse factorial. Now to invert the value, you need to calculate it power p minus 2 or modulo minus 2. Yeah. So here is my power is modulo minus 2, and here I just implement simple binary exponentiation algorithm. Yeah. That's it. So it's not hard algorithm actually. So you can implement it quite easily. I would usually copy it from the library. First, because I don't want to spend much time implementing all this stuff in every contest. Second, because if you implement it from scratch, you may have some bugs, and my library solution is just checked before. I would highly recommend to implement all this stuff before and just have it nearby. So when you have problems like this, and you have a lot of problems like this nowadays on code forces, you just copy it from your library, and that's it. Yeah. I have also all the modular arithmetic, so I have a special structure like this. You can copy it from someone else on code forces. Yeah, so you have the special structure. You don't care about these modular calculations. You just have just element and just use operators plus minus like you normally do, and it just does all the modular tricks without you noticing anything. So that's it. So this problem F. So this is so this part is actually intellectual part. Everything else is actually some library code for calculating binomial coefficients modulo m. That's it. So let's go to problem G. So what we have in problem G? Problem G is kind of interesting in some sense. So we have basically we have a graph, and we need to arrange all the elements in some strange order. So for the first look, it kind of looks like topological sorting, but it's actually not. So our graph may have cycles, but we need to put them in such order that there are no edges between two consecutive elements. Yeah. So let me show you what we have. So you order elements in some order, and you're not allowed to have edges like this from a left element to right element, but you're allowed to have edges from right to left. And Okay, it may help if you see problem like this. So first of all, you see. So they say print -1 if order doesn't exist, but there are no examples of -1. Let me show you. Yeah. So in both examples, a solution exists. So they kind of tell you print -1 if solution doesn't exist, but in both examples it does exist. It kind of suggests that solution always exists. It's not always, but usually if there exists a case when solution doesn't exist, authors kind of put it in the examples, at least one. Yeah. But here it's not. So it kind of thinks, okay, maybe solution always exists. Uh, and again, then you think why it always exists. Here it actually helps if, okay, you think what is the worst possible case? The worst possible case when I have a lot of edges. Yeah? So when you have a lot of edges, you have edges between all pairs of nodes. Yeah? So when you have edges between all pairs of nodes, you have what's called tournament graph. Yeah. So you have like edge, you have nodes, and you have edges between all pairs of nodes. So all pairs of nodes are connected in some order. So in some direction. Yeah. What's interesting about tournament graph? There are many nice properties of tournament graph. One of the nicest properties of tournament graph, it always has a Hamiltonian path. So it also in every tournament graph, it's possible to construct a Hamiltonian path. So you go from here, for example, here, and then here. Yeah. And if it is strongly connected, it is also Hamiltonian cycle also, but it's not what we have here. Yeah. So every tournament graph has a Hamiltonian path. If you know this fact before, it may actually help. If not, then it may be a little bit more tricky. Then you need to actually you need to invent this algorithm by yourself. It's also not the case. So why solution always exists? Let's think. So let's prove it by induction. So solution always exists. Yeah. So let's try to prove it by induction. So let's try to introduce people one by one. So I introduce nodes of my graph one by one. So imagine you already have some good ordering of some element. And then when you introduce one more element here, if I introduce one more element to my system, let's try to insert this element into my path. Yeah. Well, how do you insert it? It's always I claim it's always possible to insert in somewhere in my path. Well, let's try it. So where can we put it? We can put it here, for example. Yeah. It may be impossible. If it is impossible, there must be edge like this. Yeah. So if there is edge like this, let's try to put it between here. Yeah. Yeah. So this edge is allowed. I'm allowed to have edges from right to left. Yes, I'm not allowed to have from left to right in this order. So let's try to put it here. Again, it's impossible if I have this edge. So okay, if I have this edge, let's put it to the left. Again, let's find the okay. Let's move my element from right to left until I have position. So I have this edge, I have this edge, but I don't have this edge. And if you don't have this edge, you can insert here. It's possible that you have edges from all nodes. Then you can insert it in the beginning here. That's it. So that's basically that's basically the same proof of why there is a Hamiltonian path in the tournament graph. Yeah, but just specified for this problem. So that's what I will do. No, I actually implemented a slightly different algorithm because I want to have. So what you need to do, you need to check if there exists an edge, and you need to move along the current ordering and insert in the middle. And since I need to insert in the middle, I actually did it using linked list. Not the best idea, I think. Right now, I think maybe it was not the best idea, but I did it slightly different. So I did it using linked list. So what I did, I have a linked list of elements. So actually for each element, I have a pointer to the next element. And like I usually implement linked list, I have special element like virtual head of the element, and I have pointer here. So this is my current ordering. Then I introduce new element and try to insert it. And try to insert it here, then try to insert here, then try to insert it. When I find the place where I can insert it. Yeah. So I have edges here, here, but not here. Basically, I do the same, but from left to right, doesn't it? Yeah. Then I insert it in this position. So I take my element and insert between these two. Yeah. That's it. Let's see. Okay, here I'm thinking. I'm just drawing the same pictures, but worse. Here I'm having a phone call, so let's keep it. Yeah. So what I'm doing, I maintain this set. So this set will help me to check if the edge exists. Yeah. So I don't need to iterate on edges. I just need to check if the edge exists. So it's much easier to do it not using like normal like edge list like you normally do. Yeah. But just set of all edges. Yeah? So the set will allow me to check if the specific edge exists or not. So let's see. So here, okay, here I'm thinking again. What is this? So yeah. Here, what I will implement, I will do this linked list and insert my element in the middle if I can. Let's keep this. Yeah. So I maintain array of next. So it's just next pointers for each element. I maintain pointer to the next element in the list. Value 0 will be specific element just as virtual head of my list. So my list always starts in element 0. Okay? So I add this element specifically to not keep track of the beginning of the list. Yeah. Now I just do what I told you. So I go from left to right. So I start from position 0 and try to insert my element between x and the next element after x. So I check if I have edge. Okay, I decide I don't need to check this because I don't have edge to -1. So even if I have -1, it will be still fine. So if I have edge from my new element to element which is next after x, then I cannot insert here. So I need to move to the next position. And I will stop immediately because I have, in the end, I have -1. So I will not move after them. Okay, here I just draw a picture to make it clear what I need to do. So here I have element I need to insert after element x. So how you do it, you need make next of I equal to next of x and next of x equal to I. Just move this pointer here, and you insert a new element in the linked list. That's it. So that's how you insert new element in the linked list. That's basically it. Now we just need to output the result. So what I will do, I will just go use my linked list, so go from x to start from position 0 again. Every time I go to the next element, output it. And that's it. That's basically the whole code. I believe you can do it even easier, actually. That's my solution. Okay, here I have a problem because I guess yes, since I'm going from in one notation, yeah. So I need to go up to n inclusive. That's it. So that's solution of problem G. I believe there are multiple ways to solve it, but that's what I found. I believe my solution is not very complicated, so kind of approachable. Again, good for you if you solved problem G. Good result. It's interesting problem if you never saw it before, especially if you found this solution by yourself. Very good. Let's check your solutions. Interesting. So using DFS. Just normal DFS. Normal DFS. So basically you're doing the same as topological ordering and claim it works even if I have cycles. Interesting. Why does it work? Good, it's not clear for me why does it work actually. So I have all these edges from right to left, but I also have something different. Basically what's happening here, I have so if I have Okay, I have reverse graph. Doesn't matter. Mhm. So about this, then this, then this, then this. Okay, no, okay, let's make it reverse like this or something like this. Yeah. Oh, oh. No. Okay, let's go. Let's keep like so. So output in reversed order of exit time. Yeah. So I exit 4. Okay, 4, 3, 2, 1. Yeah. So I have edges from 2 to 4 to 1 to 2 from 3 to 4. Why can't I have edge from 3 to 2? Because if I have this edge, then my DFS would go here. Yeah, it's because I don't have edges from left to right in the DFS tree. Makes sense. Okay, makes sense. Okay, much easier solution actually. Yeah, good for you, good for you. You have here, you have the same. Yes. Okay, good for you. Okay, so you found much easier solution than me. Yeah, nicely done. Let's go to the last problem. Last problem is actually very difficult problem. So, okay, so what we have in last problem, we have some powers of 2, and we kind of want to, okay, if you play a little bit with what's written in problem statement, you kind of make series of powers of 2 plus something, yeah. So mm, so you have numbers, and you want to split them in some sequences. Every sequence is just some numbers of powers of 2, and then something rest, yeah. Okay, let me show you better picture than I did. So what we have? So we have some, let's say we have some power 1, 2, 4, 8, 18, and then we're allowed to have some number which is at least 32. Yeah. So here we put any number not greater than 32. Yeah. And we need to split all the given numbers into sequences like this. We need to have number of sequences. Well, if you play a little bit with this mm, with this structure, you may see that it looks like it's always better to pick more integers to a sequence. So if you try to pick, try to pick the first sequence. So if you want to try to minimize number of sequences, it looks kind of always better to just pick a lot of numbers in the first sequence. Yeah. So if you take the first sequence and put some numbers, it kind of doesn't make sense to stop in the middle. Yeah. So if you stop here and you also have number 16, it kind of makes sense to take it in the same sequence, because it will make, if you want to imagine you want to minimize number of sequences. Yeah. If you want to minimize number of sequences, it kind of makes sense to take this 16 to your sequence as well. Because if you leave it here, then some another sequence should take it. Yeah. So some another sequence may have bad time. So another sequence must take this 16 to itself. So it has more problem than you. So if you can take 16, why not take it? So if you decrease your set, you will make life for all other sequences even better. So you can easily take all the powers of 2 you can take. The interesting part happens in the end. So in the end here, you need to pick some number. So you pick all the sequences, all the sequence of powers of 2, and then you can take another element up to 32. Which element to take here? That's a question. We don't know. So we don't know which element to take, but we can take some element. Yeah? Now let's save it for later. So let's do it later. So let's first find all these sequences of powers of 2. So here we have numbers at least 16. So we don't know which numbers put here, and we have another, 1, 2. So here at least 4. Yeah. So let's keep these positions open. Yeah. So I keep these positions open. So I find all the sequences, all the sequences So you can build all these sequences of powers of 2 greedily, yes, because it doesn't look, it looks kind of natural. So if you can pick this number, let's pick it here, because some sequence need to pick this number. So if our sequence can pick number, it doesn't look optimal to stop, right? Yeah. Yes, we look again. If you go from left to right, you have two options. You can stop here or continue. Yeah, and if you stop here, then you leave this number, which should be taken to any sequence. Yeah, so if you stop here, then another sequence should continue. Why not our sequence? Let's our sequence continue. Yeah? So again, these some arguments you can think. You can prove it formally, but usually you don't do it using during the contest. Usually you just have some intuition of why your greedy algorithm works. Yeah, and then later, if you have wrong answer, then you think maybe my wrong answer doesn't, my greedy algorithm doesn't work. But if it looks intuitively correct, probably it is correct. So you train your intuition here. Now, interesting part. Now, even if we believe this greedy approach work, we need to take care of this last element. So we need to take care of these last elements. What we need to, so after we finished with all these sequences, we have some elements left. Yeah, so we have some elements left here. Let's say 2, let's say 10 and some 25. Yeah, so we need to cover this element using these open positions, and we can just do it greasily. So you have some open positions, you have elements, you can sort them, you can sort these elements and just assign them in sorted order. Just go from left to right, assign them. Okay, this is okay. This is classical greedy algorithm. If you didn't know how to do it, it's up to you. So if you need to put elements in the position like this, you can do it using greedily from smallest to largest. It's kind of obvious, but again, you can try to prove it as an exercise. It's not that hard. That's it. So I take my elements, put them as positions. Now the only question open is how to find the number of these sequences. So if I know number of the sequence, I just build the sequences, have its open position like all this. And it looks like if you make more sequences, situation is always better. So this set is increasing, yeah, set of this open position, and this set of extra elements is always decreasing. Yeah, so I need to cover less number of elements by bigger number of open positions. It will always it gets only better and better. Yeah, so you can find this number of sequences using binary search. Yeah, so the more sequences you have, the better situation you have. So at some point you have good position, and then all other positions will also be good. So that's it. So you need to find the minimal number of sequences you can have. Then all other numbers will also be approachable. So that's what I did. So let me show. Let me again. Let's read my. Let me do it. Okay. Let's again. Let's. Pop, pop. Let's make x2. Here I'm just thinking. Yeah. Thinking is a process. Now I check what is constrained. Think, am I correct or not? Looks I'm correct. Yeah. Yeah. Now I implement like this. So what I try to do, I try to pick powers of 2 while I can. To be able to do it, I need to check if I have my power of 2 in my set. So I maintain like multi-set of elements. So CNT will just count how many elements of this type I have. Yeah. Here I do just binary search. I do binary search. Again, binary search points to 2 positions. One is bad position, one is good position. So in my case, L will be some bad position. So 0 sequences is always bad. Here I think I don't need to adjust this. Yeah, I see CNT of 1 plus 1. So if it is possible, it should be possible. So maximal number of sequences you may have is just count of elements 1. Yeah, so you can have as many sequences if you have ones in your set. And I do CNC 1 plus 1 because maybe CNT 1 is still bad. So you need to pick some value which is definitely good. So I put some fictive value. I will never check it. Yeah, but I'll put my basically how you make binary search. You make this pointer out of your array 1 position. So maximal number of sequences I may have is CNT of 1, and I move my right pointer 1 position to the right. Yeah, and here normally binary. There's just normal binary search. Yes, here I'll just implement binary search. So now I need to check if this value is good or bad. So I will go and just greedily find all these sequences. So I just start from here. Here I'm thinking what is the best way. So I will put all these extra elements to speed special array A. Let me see. So again, I check if I have this power of 2. I take it, so I decrease the counter and move to the next power of 2. And I just put all these elements to array A. So array A contains all the last elements of these sequences. Here, yeah, and here you need to check that you can cover all the remaining elements. So I will iterate all the remaining elements. So I have, okay, element X is my remainder element, C is number of, yes. So I iterate over C elements of equal to X and check if I can cover them or not. Here I make a mistake, I will fix it later. Okay. That's it. So here I have -1, I check why I have -1, here I have a debugging. Okay, it's kind of embarrassing, but it's again, uh, sometimes you have mistakes and you have to debug. That's how I usually debug. I output a lot of values and check if I can. So I have values 6 and 2, and I need to cover 3 and 5. Okay, I can cover 3 and 5 with value 6 of 2. So okay, that's because I output the last value. I need to have value which is next power of 2, which is, so my remaining element is not greater, let me show you, than the next power of 2, which is not in my set, this next power of 2. Yeah, so I need to put this element to my set. So I change this. Hey, I still have -1 because I can. Okay, yes, because my array is sorted in the wrong order. Yeah, so my array A is sorted in decreasing order, and and I check elements in increasing order. Yeah, so you need to reverse this array. So now both arrays are in increasing order, so you're fine. That's it. Check this. You check this. Yes, you submit, and then I will have a mistake. Can you find the bug in my code? Okay. Okay, I'll have wrong answer test 10. Okay, yeah, this program has wrong answer test 10. So if you can pause this and find the mistake. No, it's okay. It's easy mistake. I read the code multiple times. Okay, I'm just reading the code. What I normally do when I have a mistake, I first read the whole code and try to check if it does what I expected to do. Then sometimes I check my assumptions. So I assume that binary search work. It looks correct. So I thought a little bit. Then binary search looks correct. Yeah. Then I can read the code and check if it does what I expected to do. And then I will find a mistake at some point. Okay, okay, I read it. Okay, reading the problem statement also helps. So maybe you missed something from the problem statement. I'm not missing something from the statement. Okay, so I read the code multiple. So here is the problem. Okay, here. I'll tell you. So here I forgot to skip all. So I try to match element from left to right, but sometimes you have more elements. So you need to skip elements here. So here you need to find element in array A which is greater or equal to x. So you skip all elements less than x. Yeah, and then you pick the element if you have one. That's it. So that's it. That's problem H. Again, probably a little bit harder from this code, but okay, I think it's not that hard. So it's solvable. Yeah. So all steps are kind of approachable, let's say. Yeah. So let's read your solution. So you solved it in upsolving. Okay. Okay. Read elements and solve. I'm empty. Okay, I don't see binary search. I don't without binary search. I believe it's C++. No, B. Interesting. So it's maximal power of 2, I believe. So count powers of 2. Calculate prefixes. DP. Interesting. It's a nice solution. I'm not sure what you're doing here. So since I'm dynamic programming, I'm not sure what it does. Boom, 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 boom. So you put some pairs. So you make this type of dynamic program when you put some pair of element and you move forward. So what this pair contain? Uh, 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 uh. Okay, so you make that over number of. Interesting. I think what you does here, I believe, is you check how many. So you take some power of two, check how many these powers of two. So basically, you split all the sequences in different lengths, and then just take all sequences of the same length, probably. And you want to kill as many elements as possible. Yes, something like that. Good for you. No, it's actually if it works, it's great. Uh, Good for you. If you manage to solve this problem using some type of dynamic programming, good for you. It's actually uh, much more safe usually to solve dynamic programming than some greedy algorithms with some strange binary searches. So you need to be sure that your binary search works. You need to be sure your greedy algorithm works. If you can solve it using some dynamic programming, it's usually much more safe. So good for you, something like this. Good. So that's it. That's contest 16. Yeah. So thank you for watching. See you next week.